Hello, and welcome to Astronomy 100. In this video, we're going to continue our discussion of galaxies. In previous videos, we've discussed a couple of ideas related to the concept of galaxies. First of all, it's important to understand that the Sun and all the planets that go around the Sun is located inside of a big galaxy, big collection of stars that we call the Milky Way galaxy. And in our previous videos, we've talked about some of the details about the structure of our galaxy, how we know its size, how we know its shape, how we know some of the details about what we find inside of the Milky Way galaxy. And even though in our modern world we understand the concept of galaxies, there are many, many galaxies in our universe, one of the things that had to be answered early in the 20th century that seems like a trivial question today turns out to be one of the biggest questions of all of modern astronomy. So let's go ahead and talk about that here today. So in our first picture here, this is the picture that we've been seeing as our splash screen. And what you can see is that it's a picture or an image of many, many galaxies. Lots of different shapes, lots of different sizes. But with hindsight, of course, today we know that each of these fuzzy blobs are galaxies, very much like the Milky Way itself. If you can imagine, there was a time, though, early on in the 20th century when we were taking photographs of these fuzzy objects, it was not automatically assumed that these were galaxies like the Milky Way. In other words, in astronomy, there are many things we have to actually prove. We can't simply assume. And so the idea of, is this a picture of a bunch of spiral fuzzy objects in our galaxy, or is this the picture of a bunch of galaxies like the Milky Way, and maybe the Milky Way is just one of many, many galaxies? And this was a controversy early on in the 20th century. We'll get to that in just a minute. But let's first talk about one of the tools that will be eventually used to resolve this controversy. In the late part of the 19th century, in the late 1800s, we're talking 1893 or so, a young woman by the name of Henrietta Leavitt went to work for Harvard Observatory. And one of the jobs that she was given was to simply look at photographs that had been taken by the observatory of lots of different stars, of lots of different types of stars, and to catalog them based on their qualities. Now, Henrietta Leavitt started to notice that there was a particular type of star that had been studied in years prior that had some features to it that could help us understand one of the biggest problems in astronomy, and of course that's the idea of determining distances. Let me show you what I mean. In the last few centuries, we have been well aware of a particular type of star that its progenitor, or at least its namesake, comes from the fourth brightest star in the constellation of Cepheus the King. This is the star called Delta Cephei. Now, Delta Cephei is a type of star that we call an intrinsic variable star, meaning that variable means that it changes its brightness. Intrinsic means is that the star itself is physically doing something to change its brightness. And so over here in this animation is an example. This is a type of star that is just like the star Delta Cephei. And this star is, you'll notice as these pictures are going through time here, you can see the dates changing down here, and it's just repeating. You'll notice that the appearance of the brightness of the star is changing, hence the name variable star. And these types of stars are called Cepheid variables after the namesake of the very first one discovered, called Delta Cephei. And this is a graph down below showing you how the brightness, so visual magnitude is the appearance of brightness to our eyes, how the brightness of Delta Cephei is changing over a period of time. So this is days going by, and this is the appearance of brightness. And you notice that each dot is in a slightly different place. Each dot is one observation, and you can see that when you look at this star for many, many days, you can clearly see that it becomes fainter, and then it becomes brighter, and then it becomes fainter, and it becomes brighter. And it's repeating this over and over again. There's a period of time that it takes to go through becoming bright, then the faint, and then starting all over again and becoming bright. So there's a period to the change in its brightness. Now, Leavitt noticed that there are lots of stars that do this. And when she started to look at the period of time that it takes for a star to do this type of a variable star, and the change in its brightness, she started to notice a particular connection. And in particular, she was studying Cepheid variable stars in a galaxy that is actually right next to the Milky Way. This is a photograph of what we call the Large Magellanic Cloud. It's a sort of a neighbor small galaxy to the Milky Way. We can't see it from the northern hemisphere. You have to live in the southern hemisphere to see it. This photograph here was probably taken from, let's say, somewhere in Australia. And this particular galaxy is home to many of these Cepheid variable stars. And so Henrietta Leavitt was sort of taking these images that had been taken by the observatory. She was documenting all the information about these variable stars. Now over here on the right, you can see 4 examples, and each one of these is a Cepheid variable star. And what you'll notice is that the brightness of each of these stars is changing over time, so bright, faint, etc. They're all doing exactly the same thing, bright, faint, faint. But you'll notice that the period of time that it takes them to change their brightness is different. Some stars change their brightness very rapidly, becoming brighter and fainter and brighter and fainter in as short as maybe 1 day, going from the peak in brightness to back to another peak in brightness. Or some of them might take as long as 100 days to change their brightness. So each of these variable stars, these Cepheid variables, is changing their brightness over time, but some of them take a long time to change their brightness, and some of them do it very quickly. Well, Henrietta Leavitt discovered that there was a relationship between the period of pulsation, which means how long it takes to become bright and then faint and then bright and then faint. That's the pulsation. So the period of pulsation of the star was inversely related to the luminosity of the star. Remember from a previous conversation or video that we had earlier in the semester that luminosity is the amount of energy that the star is actually producing. So the amount of energy that the star is producing on average for these types of variable stars is related to the pulsation period. Now the idea is that when you look at the stars in the sky, by measuring their brightness change over time, you get the period of pulsation. And from the period, you could determine or infer the star's average luminosity. Now the reason why that's critical is because if you know how much energy the star is actually producing, and you can compare that with how bright the star appears in the sky, then you can determine the distance to the star. In a previous video, we talked about what was called the distance modulus, which is the brightness of the star, the amount of energy that the star produces, and the distance, and how these 3 things relate. So as long as you know the appearance of the brightness of any star and how much energy it produces, you can always determine its distance. So what Henrietta Leavitt has sort of inadvertently discovered is a way to determine the amount of energy that a Cepheid variable star produces, and from that, comparing with brightness, we can get the distance. Now the reason why this period luminosity relationship is so very critical is because when you look at the Large Magellanic Cloud, we don't know how far away that is. What we can do is measure the period of pulsations of the variable stars in this grouping, in this galaxy, and from that we get the distances to those Cepheid variables. Now obviously the Cepheid variable is contained within this galaxy, so by measuring the distance to these variable stars, you are measuring the distance to this galaxy. So as long as you can find Cepheid variable stars in galaxies, you can determine the distances to those galaxies. So the summary of this is that the period luminosity relationship allows us ultimately to determine the distances to various objects in our universe, which is a very, very critical thing to do. Now, this is all related to a particular debate that took place in 1920, and it took place at the Smithsonian Natural History Museum. And it was between two very famous astronomers in the day. The man on the left is Harlow Shapley. We've discussed him in a previous video. And the man on the right is Heber Curtis. And each of these two held a different position about these spiral-shaped clouds that were seen in the sky. This is a photograph taken in the early part of the 20th century, and it's very hard to read, but you can see that it says spiral nebula in Andromeda. And this was believed by Harlow Shapley to be just a cloudy thing inside of our Milky Way galaxy, and that the Milky Way galaxy was the entire universe, nothing outside of it. So these fuzzy things were in the Milky Way galaxy. Heber Curtis believed that what we were actually seeing were galaxies unto themselves, and that the Milky Way is just one of many, many galaxies. So there was a debate in 1920 as to whether the answer is there are many galaxies in our universe, and the Milky Way is one of them, or that there are simply spiral nebula-shaped clouds in the single galaxy of the Milky Way, which was the entire universe. In other words, the entire universe was just the Milky Way. Now, there was no real winner of this debate, but the reason why this is significant is because it turns out the ability to detect Cepheid variables in one of these fuzzy-shaped spiral nebulae would be the key to the answer. And sure enough, in 1924, Edwin Hubble, of course very famous today because of a telescope named in his honor, Edwin Hubble used the biggest telescope in the world in its day, in the day of 1924, and was actually able to discover Cepheid variables in the quote-unquote spiral nebula called Andromeda. And of course, by discovering these Cepheid variables in this particular spiral nebula, he was able to determine, using the period luminosity relationship, that the distance to these Cepheid variables was a distance of several million light years. And that means the thing that contains them is also several million light years away. Now, the problem is that the Milky Way galaxy, or the Milky Way, is not several million light years in size. And so the distance to this thing was much further than the size of the Milky Way, thus proving that this is actually not something in the Milky Way, but is something outside of the Milky Way. And so it was in the early 1920s that we finally had conclusive proof through a measurable technique that these fuzzy spiral-shaped objects are actually galaxies unto themselves, and that the Milky Way is a galaxy just like all these other objects we see in our universe. So in the 1920s, our universe grew from being one big Milky Way with lots of things in it, and that's it, to suddenly a much bigger universe with lots and lots of galaxies, the Milky Way being just one of them. Now here's a final example. The galaxy called M100, photographed here on the left, also contains Cepheid variable stars. And you can see here's 3 frames of this Cepheid variable that's becoming brighter and fainter. And using the period luminosity relationship from Henrietta Leavitt, we now have the ability to get the distance to this galaxy, and using that relation, we can figure out that the galaxy M100 is 55 million light years away. So a young woman working at Harvard Observatory, and in the day of the 1890s, there were not many women working in astronomy. So this is quite an important step forward made by women in science. And in the late 1890s, we can now see that through the hard work and the critical thinking and ingenuity of a young woman working at the Harvard Observatory, she was able to discover one of the most important tools used by astronomers, the discovery that Cepheid variable stars have a relationship to the change in their brightness over time that is related to the amount of energy that they produce, unlocks what we call a distance measurement technique. And as long as we can find a galaxy that happens to have Cepheid variables, we can measure the variables, get the distances to those galaxies. So we now can start to measure the distances to neighboring galaxies and start to get an idea of what the structure of our universe is like, more than just the structure of our Milky Way. In our next video, we're going to talk about how the galaxies themselves, now that we know that they are individual galaxies, have different shapes and sizes and what information we can learn from that. We're just about out of time, so I hope you'll join me for that next video. We'll see you then.